Hey guys, welcome back. So today we're going to be looking at what the second derivative does, how we find the second derivative, and also how we find these things called points of inflection. Okay, so let's have a look at this graph. Well, to start with, I've written that this graph has an equation of y equals fx. Now, if you're not familiar with this expression, really this is just me saying that y equals some kind of equation that isn't important. Don't worry whether it's y equals x cubed plus x squared or y equals x to the 4 minus 3x squared. It doesn't matter. It's something. It's some kind of function. It's got an equation that you don't have to worry about. That's what that means if you see that. Now, with this graph, I've drawn a tangent here at this point when x equals 3. So at x equals 3, drawn the tangent, and we know that if we want to find the gradient of that tangent, if we want to find how steep the curve is at that point, at that exact point, then we use the first derivative. And we can just replace x with 3 in that derivative equation. Okay, but what about when we want to use the second derivative? Well, the second derivative is going to be used to tell me how much the curve is bending at this point, right here. I know that the first derivative is going to tell me how steep the curve is at that point by using this tangent. It's going to tell me what the gradient is. So it tells me how steep the curve is. But the second derivative tells me how much it's bending around this point. It tells me whether it's bending down or whether it's bending up. You can see here that this curve has 3 different parts in terms of its concavity. And remember, concavity is talking about how the curve bends and what way it bends. Over here, we can see that it's bending down. This part here is concave down. This part here is bending up. It's concave up. Right? The curve is pointing up. And back over here, we know that it is concave down. And we were particularly looking at that point. So this part of the curve is obviously concave down, and it will be all the way down here. This part of the curve is concave up, and this part of the curve is concave down. So it's talking about how much the curve is bending. Now at this particular point, if I want to find the second derivative, I am finding how much the curve is bending at that point. What about at a point there? It might look like it's bending a lot, but it's not much at all. Okay? Because when I draw the tangents, I'll draw the tangents up here. There's a tangent at that point. There's a tangent at that point. Is there much of a difference between these tangents? No, they're almost the exact same gradient. And the second derivative tells you how much steeper the curve is getting. Does it get much steeper there? No, there's barely any change. So when you hear that derivatives are all about the rate of change, what it's saying is, for the second derivative, is how much is the first derivative changing as I move from this point to this point. As I move my x from here to here, from here to here, how much does the gradient change? Because that's what the second derivative does. The first derivative tells you how much the y changes. It tells you that at a point, how much is the y going down or how much is it going up if I move x a bit to the right? Because we know that the gradient or the derivative is just the rise over run. So the first derivative tells you how much the gradient, how much the y or the height is going to change if I increase x. And the second derivative tells you how much the gradient or the first derivative is going to change as I increase x a little bit. Okay, so over here, the tangents had barely any difference. What about as I move from this point, there's the tangent, to this point? Well, this one has quite a flat gradient. and this one is quite steep. So there is a big change between those two derivatives, and we can see that it means that the curve is bending more there. So the more the curve bends, the more the derivatives at those points are changing, and that's what the second derivative tells you. Okay, so the second derivative is obviously going to be positive when our curve bends up. So for all these points around here, we're going to get a second derivative, and I'm giving it the symbol of y dash dash because it's just the derivative of the first derivative. Y dash dash is going to be positive. But here, y dash dash is going to be negative because it's pointing down. Here the curve is bending up. Here the curve is bending down. So over here again, the second derivative is going to be negative. Okay, so let's look at an example to see how we can find the second derivative. So let's say we have the equation y equals x cubed plus 2x squared plus 3x. Well, we know to find the first derivative, we use our rule and we move 3 to the front here, 3x, and we minus 1 from the indices to get 3x squared. So I move that to the front and I minus 1. And I do the same thing over here. I move 2 to the front and that's going to times the other 2. So I'm going to get plus 4x and I take away 1 to just get x because it's x to the 1. And then I know that when I've just got an x term by itself with no power, it is just the number in front of it that is the derivative. So that's our first derivative. Now I can sub in any point like at 3, and this equation is not for this graph, but I could sub in a point here for this equation, and I could find what the derivative is at that point. So I'm going to sub in x equals 1. So at x equals 1, the derivative is 3 times 1 squared plus 4 times 1 plus 3. So the derivative is 3 plus 4 plus 3, which is 10. So it has a gradient of positive 10, okay, which is very steep. That is like maybe steeper than that. Okay, what about the second derivative? And remember, I'm just doing y dash dash. This is the derivative of this. So that's our first derivative. Now I'm going to do the derivative of this equation, not this equation. We've already done that one. So to derive this, we use the same rules. Bring the 2 down, which is going to be 3 times 2, which is 6, and 6x, because we minus 1, plus 4. And then plus 3 doesn't have a derivative. So now we have the second derivative. So now if I substitute x equals 1 into this equation, I'm going to get y dash dash equals 6 times 1 plus 4, which coincidentally is 10. Now that is just a coincidence. That is just luck that they are the same. If I did different points, you'll probably get something different. Let's say I substituted instead up here x equals minus 1. Well, now I'm going to get y dash equals 3 times minus 1 squared. And we know minus 1 squared is just 1. So we get 3 minus 4. And I'll show you how I'm doing this. I'm doing 4 times minus 1 plus 3, which is going to equal 3 minus 4, which is minus 1, plus 3, which is 2. Down here, if I substitute x equals minus 1, I'm going to get y dash dash equals 6 times minus 1 plus 4, which equals minus 6 plus 4, which is minus 2. So the second derivative is negative, but the first derivative was positive. So we know the first derivative had a positive slope. So let's say basically, let's say we're on a curve that looks like that. We're at a point where the derivative is 2. There's the tangent at that point. But the bend, it's bending down. Like over here, we saw that this was bending down. That's why it's come out negative. And the derivative is changing, so the derivative is getting steeper by 2 at that point. Or flatter, I should say. The derivative at this point, if I move it a little bit across, is going to get flatter by 2. The derivative is going to change by 2 at that point. So you can see here that it's only negative in the second derivative because it's bending down. In other words, it is concave down at that point, but the gradient is increasing. It's still increasing, but it's increasing at a decreasing rate. It is slowing down. It's getting flatter. That's what this tells us. That's why that is positive and that's negative. It's getting bigger. Y is getting bigger, but it's getting bigger much slower. You can see here it's starting to bend around. The derivative is soon going to equal 0 at that point. Okay, hopefully that makes sense. Go back and listen to that again to make sure you understand that. All right, so now you understand what the second derivative does. It tells us how much the gradient is changing. Is the gradient getting steeper at a point, or is it getting smoother? And is it on a part of the curve that is concave down, where it's going to be negative, or is it on a part that's concave up, where your second derivative will be positive? Okay, so the last thing that is really important, and we're going to look at this graph again, and I'll make some more room here, is when does the curve or the concavity of the curve change? We can see here that the curve's concave up, and we can see here that the curve is concave down. When does it change from being concave up to concave down? Well, if you imagine this concave up bit is going to go up to about here, and then if I don't look at that, the whole curve looks concave down. If I block that out, it's concave up. So it's about at this halfway mark, and that's not the rule. It's not always halfway, but it looks like it's just about there that the concavity changes. There is a change in concavity. That's where it changes, right? So y dash dash would have gone from being positive to negative, which meant it would have to equal 0. And we call this point where it goes from being concave up to concave down a point of inflection. It is called a point of inflection. That is where the curve goes from bending up to bending down. That is the actual point where the gradient at that point is not changing. There's no change in gradient there, okay? It's so steep that it doesn't change at all there, okay? All right, so how do we find this? Well, to find these points of inflection, we get an equation and we make the second derivative equal 0. So let's go back to our other point where we had that equation y equals x cubed plus 2x squared plus 3x. And we remember that the second derivative, I'll go straight to it without using the first derivative, was 6x plus 4. Remember, this is not the equation for this curve. But if I want to find the points of inflection or the point of inflection, there's only going to be one here for a curve, I make this equal 0. So remember that, I make that equal 0. I want 0 to equal y dash dash. Okay, so I'm going to put 0 equals, and we know y dash dash is 6x plus 4. So I put that in here, and now I solve it. Okay, so we know the opposite of plus 4 is minus 4, and I'm going to put that on this side. So minus 4 equals 6x. I'm going to switch them around here. 6x equals minus 4. So then we divide by 6 to get x equals, I'll simplify these, 2 over 3. Minus 4 over 6 is 2 over 3. We get minus 2 over 3. And that's going to be the point for this equation, not for this curve, where the concavity is going to change. It's going to suddenly change. The curve's going to go from bending up to bending down. Okay, and the last thing you do would be make sure to, because you're going to find the point of inflection, you need to find the y coordinate. So we're going to substitute this value back into here. All right, guys, keep watching in the next video.